So, today's lecture, Intermediate R with Chuck. Okay. So, overview for today. Today is going to be focusing sort of on data management using what I call, and many people call, the sort of best practices or the industry standard sort of packages for data manipulation, data cleaning, joining, and that kind of thing in R, which are all centered around this thing called the Tidyverse. So the packages used today are all inside of something called, it's working, oh that's right, I can't point at this with the laser. I'll just point with my fingers, okay. Are inside of the Tidyverse. So the Tidyverse is two things. One is it is an R package. If you do install.packages, you will get the Tidyverse downloaded. But Tidyverse in reality is actually a very large collection of many different packages that are done, that were generated by a group of people who work together and are sort of loosely affiliated into an organization to make packages that have very similar syntax, a similar approach to data. They all play very nicely with each other, and they're very well updated and have a lot of thought put into how all of the functions work and how they play together. So every package in the Tidyverse plays very nicely with every other package in the Tidyverse. They tend to play well with other packages outside, and they're so dominant in the world of R that pretty much everyone else making packages makes them play nice with these Tidyverse packages. Okay. Yeah, they share a design philosophy, they share syntax, they share data structures. It includes some packages that even if you're not that familiar with R, you may have heard of or you know people are using. Things like dplyr, ggplot, tidyr, and a bunch of these other ones are packages that are sort of part of the Tidyverse and are very commonly used. Okay, you can install the Tidyverse in R just with install.packages Tidyverse. We're going to use a couple other packages today too that just contain data sets I'm going to use in quick examples. These data sets are Gapminder and NYC Flights 13. Gapminder has a bunch of panel data on nations with indicators like life expectancy, GDP, and things like that. NYC Flights 13 has a snapshot of every flight, I believe, that flew out of a New York City area airport in 2013, but it's composed of 6 different data sets. I'm going to use it for examples for joining different data sets together. Okay, it's not important that you remember any of these things, but that's what's going to happen. I'm going to open up here with subsetting with dplyr. So subsetting with dplyr will introduce sort of the basic mechanical stuff you would use anytime you're working with data in R to replace most of your base R functions. So all that nice stuff that I taught in the first lecture about subsetting and stuff, we're going to replace it entirely with a system that's easier to use. Okay, the first thing I want to talk about though, before we get into actually subsetting data, I want to talk about pipes. So dplyr and the Tidyverse in general works with something called the Magritte forward pipe operator, which people tend to just call the pipe. What it looks like is percent greater than percent. So it's like an arrow in between 2 percentage signs pointing to the right. There's shortcuts on Mac and PC. If you were on a PC, Control-Shift-M will insert a pipe, in RStudio that is. And on a Mac, Command-Shift-M will insert a pipe. So you don't have to keep typing percent greater than percent. Okay, so right through the text. Okay, so pipes take the object on the left side of the pipe and they apply whatever function is on the right side of it. So you would read it something like, let's say X is on the left, you'd say X and then do function to X. But you can chain these pipes together over and over again to run many functions in a row. Here's an example. If I had loaded up the dplyr package, I load up my Gapminder data we're going to use in a bit, I could say, let's start with Gapminder. Gapminder is a data frame. It contains all the observations in the data set. I pipe it into the filter command. The filter command I'm saying there, country equals Canada, says I want to take the data, but I want to keep only the observations that are from Canada. Okay? Then I pipe it again and say head 2. Head is give it a number and it tells you, or it tells it how many observations to display from that data set. So I've taken my data, filtered it to something, and then displayed 2 observations. The output is below. So you can chain an arbitrary number of functions together without creating some intervening object, and most importantly, without nesting them inside of each other. So if I wanted to do this in a conventional R way, I would have to say head, filter, Gapminder, country equals like Canada. They'd have to be inside one another. Pipes read left to right, top to bottom. Normal R functions read inside out. I'm not familiar enough to say for sure, but I'm pretty sure there aren't any human languages that read inside out in all of their sentences. Right to left is possible with pipes, left to right possible. Much more intuitive for most people. Okay. Pipes save us typing because we're not constantly creating objects and calling on objects we already made. They make your code more readable by making it left to right, and they allow chaining. So we're going to use them all the time when manipulating data. In fact, I use them all the time for just about everything. Most of my projects, the entire pipeline of stuff that takes the raw data, maybe even downloads the raw data, does all of the processing, everything until the final data used for my plots and models will be in a single chain of pipes. There might be 100 function calls in that chain, but I can just read it, see, we're going to start here, do this, then do this, then do this, then do this, then do this. At the end, it finishes. Pipes like that never create an intervening object, and it's very clear how everything happens in a sequential order. We'll see a little bit of that. Okay, so using pipes, my opinion, pipes are clearest to read when you have each function on a separate line. It'd be something like, we take these data at the start, we do a first thing with some value, we pipe it to the next line, we do the next thing with some value. It's not real R code, so if you attempt to write, it's going to yell at you. But you could do this and just keep going on and on and on and on, line by line. Stuff to the left of the pipe gets passed to the first argument of the next function. So every function in the Tidyverse, for the most part, its first argument is a data frame, and the output of every Tidyverse function is usually a data frame. Data frame goes in the left side, comes out the right side, ready to go into the left side of another function. If you ever find yourself piping data or piping something into a function where the data are not the first argument, pipe operator looks for a period inside of the function call. Here I see data equals period. Instead of piping the data gapminder on the left side into the first argument of linear model's first argument is a formula. Instead, this is saying, I want to pipe it in over into data. I put a period there. Whatever you pipe into it goes to where the period is. Make sense? See a couple examples of it. It's not super important because most functions today, data is the first argument. Okay, so if you want to use a pipe and a whole chain of things and create an object in the process, you do the assignment before you even start writing that chain of functions. So if I want to create a new object from the output of something I've piped, I would place the assignment operator at the very beginning. So I'm saying I'm going to create a new object called lm_pop_year, a linear model of population to year. I pipe my gapminder data into my linear model, pop_year data. No matter how long this chain is, it's going to assign back to the object at the beginning, which is kind of intuitive if you think about it. What you want to say is, okay, I want to create some object called this, and what I'm going to use to create it is all the stuff that comes afterwards. The logic of it begins with, well, I want to make an object. You don't say, I'm going to do all these operations, and at the end be like, oh, and by the way, I want to make something out of it. Right? So it's done at the beginning. Okay, so I used the filter function earlier as an example. Filter's a pretty intuitive function. In dplyr, if we want to subset the rows of our data, we can do it with logical conditions, logical statements in the filter command. Filter is a way to subset specific rows in your data. If you're used to base R functionality with a bracket subsetting, think of filter as operating on the first location in the brackets. Like a data frame has two dimensions. It has rows and it has columns. Filter operates entirely on the rows. There's a totally different function for subsetting columns, because in the Tidyverse, rows are always observations and columns are always variables, so you subset them in different ways. So the way filter works is I would take some data frame I want to do some subsetting on. Gapminder, I pipe it into filter, and then I say here, country equals Oman, then I pipe it to the head function. What do we get down here? Every country, every observation here, its country is Oman. I didn't have to say, look back in the in gapminder and filter, because filter knows we've already sent the gapminder data to it. It knows that I want to check that country is equivalent to some value. It works, it produces it. Is everyone familiar with what's going on with that country equals? Okay, it's a logical expression. Logical operators will test some kind of Boolean condition, and they will return a true, a false, or an NA. The way filter works is you put some condition up in filter. Anytime that condition is true for a row, it keeps that row. Anytime it is false, it drops it. If it checks and gets an NA, it will yell at you, usually. So, what we used in the last slide, we used equals equals for testing to make sure country was Oman. There's a lot of other logical operators you could use inside a filter to do tests, maybe things with numeric variables and things like that. One of the common ones is saying not equal to. Maybe I want every observation in this data set except Oman. I could replace it with exclamation point equals. It would make it everything but Oman. So that's not equal. You could do greater than, or equal to, less than, or equal to for numeric things. I'd say I want every variable in the data set that is below the mean or below the median, right? You could use %in. %in is for doing multiple equality checks, which I think I've got a slide on here in a minute. We can also do combinations of logical conditions. So we could have two logical conditions and say both of them must hold, that is and. Only one of them, one or both of them need to hold, is or. We could also invert an entire series of logicals. If you take a bunch of logical conditions and put them inside parentheses, if you put an exclamation point in front of them, it will invert all of them. Okay. Sometimes you want to use an inversion of that of a logical condition. Sometimes it's easier to think of a negative case or a positive case for some particular thing and flip it over than to think of the exact thing that you might want. Okay, so let's say that we want all the observations from Oman after 1980 and through the year 2000. We don't need to do multiple filter commands to do this. We can just say, take the gapminder data, pipe it into filter, say country equals Oman like before, and year is greater than 1980, and year is less than or equal to 2000. It will do all of those happily at the same time and produce a data set that is the 4 observations in Oman that occur after 1980 and before the year 2000. That's straightforward? Yeah. I think the syntax is pretty easy for filter. It's one of the reasons I think it's a lot better than sort of normal subsetting. It just kind of works and it's very intuitive. Okay. You could also, instead of saying and there, if you put commas in between logical conditions, it will treat them like they're ands. I usually put ands because it's more explicit to me. We could also do something like replace those ands with ors, and then we would get every single year of Oman, and then we would get every other country. Actually, we'd get every single observation in the data set, because one way or another, every observation in the data set is either greater than 1980 or less than or equal to 2000, because those are on opposite ends projecting forward and backward. So you probably wouldn't use ors. Okay. Here's an operator that's really useful inside of filter commands. Very often we want to do something like, okay, I want, say, a subset of countries, and it's these 5 or 6 countries that I want. In this case, I want all of the former Yugoslavian countries, Bosnia and Herzegovina, Croatia, Macedonia, Montenegro, Serbia, and Slovenia. I assign those as a vector to something called former Yugoslavia. Then I say, I'm going to create a new object called Yugoslavia, which is the gapminder data, filter country %in former Yugoslavia. This says, okay, anytime country matches any of the countries in former Yugoslavia, it will return a true. If it does not match one of those, it will return a false. This is a way to quickly filter and get every single one of the former Yugoslavian countries. I do a quick tail on here. Tail is like head, but for the bottom of a data set. And I see that I got 2 countries from Slovenia. If I've gotten Slovenia here, so long as I've typed the other ones correctly, it probably worked for the rest of them. Didn't want to display them all at once. Yes?
Quick question. So when you say head, if I were to say head Yugoslavia 2, it'll show me the top 2 observations.
The top 2.
This is showing me the bottom 2 observations.
Yes. Yeah. Head is the top 2, tail is the bottom 2. Yeah. Well, it's the top or bottom, whatever number I give it. You could do head 100, it will give you the first 100 observations, so on and so forth. But yeah, absolutely. Head and tail are some of the most useful quick check functions. Like as soon as I make any kind of an edit to a data set, I'll usually immediately look at the first 6 and the last 6 observations. Because if I messed up something, it's usually at the beginning or the end, or in every place in the entire data set. That's the most common. Okay, so often we want to sort our data. Just for displaying it and looking at our data, we want to sort it in some way. In dplyr, there's a function called arrange, and arrange can take any number of arguments, and those arguments are variables. In this case, I'm saying, okay, what I want to do is I want to get these Yugoslavia data I created in the last slide. I want to arrange them ascending by year and descending by population. So it's going to order them first by the year in increasing order. Then within each year, it's going to make them descending by population. If we look over here and see, we'll see all of the 1952. So there's 5 observations in 1952. But then within that year 1952, it starts with the highest population, goes down to the lowest population, then to the next year up, highest population. You can chain any number of those arrange commands to arrange it in some particular way you want. Yeah. Straightforward. Next, subsetting columns. So we can subset rows with filter. You can come up with all sorts of interesting ways to use filters, but use an entirely different function if you want to select specific columns, because columns don't describe your observations, they describe your variables. We want to use different techniques to sort them. We usually don't want to do things like select columns based on them having a name that's greater than or less than something. Our columns are not usually numeric in value. They're usually like words that mean something, right? The way select works is we say Yugoslavia, pipe it into select, and then we can just write out the specific variables we want. Notice their names are not in quotes. Most of the things in the tidyverse will handle quoted or unquoted variables. It's something referred to as non-standard evaluation. It's rather uncommon in programming, but it makes it easier to write, so you don't have to quote everything before it goes in. This is me saying, I want those Yugoslavia data, but the only variables I care about are country, year, and population. Then I pipe it into head, and we see all I have is country, year, and population from my former Yugoslavian country data frame. Okay? Straightforward.
So this is only in Tidyverse that you can use the select without the quotes.
Yeah, any kind of variable. So select only works on columns.
Right, but even if I use select outside of Tidyverse, I would have to put it in quotes.
Well, the select function that is inside of the tidyverse is in dplyr. It is different than the select function that is not in the tidyverse. So there's a select function in the mass package, MASS, that does very different things. Do not load the mass package in full at the same time as like dplyr is loaded. They will conflict, and you get very confused when select starts giving you things. But if you use this select function without piping into it, you can still select this way without unquoted variable names. However, if you were doing subsetting by brackets, like at the end of if I did gapminder bracket and then I was subsetting by the names, they would have to be quoted.
Likewise, is piping only in dplyr or in the tidyverse in general?
No,
or in R in general?
R in general. Actually, no, not even R in general. So I'm glad you asked. So the pipes are actually a very old programming thing that sort of date back to the original introduction of Unix. So one of the things that made Unix so powerful on the command line, particularly the bash shell and things like that, if people are familiar with this, was that you could run some function on something, and without saving or generating the output, you could just immediately pipe it into something else. So like in a bash terminal, the OR operator, the vertical thing, is called a pipe, and that's what it does. You do some function, pipe, and then it just sends it to whatever's the next one, so you do a whole bunch in a row. This was actually people being like, well, we do all this Unix functionality on the shell and having a pipe. And the people who use R were like, why can't we just pipe things in R? And so they came up with this convoluted way. Like if you look at the way the pipe operator is written in R, it is really complex. Because it's not actually sending the things from the right or the left to the right. Instead, what it's doing is it's gathering every function call you make in the entire chain and reassembling it inside out behind the scenes and then putting the output out. It's very complicated. But because of the way it works with any functions in R. Anything in R you can send in pipes. It's just easiest when data or something is its first argument. But I routinely pipe model results. Models produce lists usually in R. I pipe my models into things all the time. I pipe everything. Everything is just a pipes. If I have time at the end, I'll bring up like one of my scripts off my GitHub, and you'll see I've got pipe chains that are handling all sorts of weird objects. They're actually they're not usually that long. Most of my stuff is quite compact. But I have a really complex project where I've got maybe 40, 50 function calls all piped in a row, but the object types are varying all over the place. What finally pops out is a combination of tables, plots, and PDFs and stuff, but it's all going through like pipe chains. You can pipe anything. Anything you want to go from the left side to the right side, you can pipe. Yeah, okay. So this is select, but very often what we want to do is we want to not say I want only 1, 2, 3, 4 variables. Maybe I want like 20 variables in a data set of 23 variables. I just want to get rid of a few. Select can also do negative selection. So we could drop specific columns by doing select and just putting a minus in front of the variables we want to get rid of. So perhaps I want all my Gapminder data, or in this case my Yugoslavia data, but I just want to get rid of continent, population, and life expectancy. I just say minus continent, minus pop, minus life expectancy. What I get is country, year, and GDP per cap, the other 6 variables in the data set. So you can do positive selection or negative selection. You can obviously not do both positive selection and negative selection at the same time, because they're opposites. But yeah, you can do positive or negative. Sound good? Yeah, straightforward, like filter. Okay, there are a lot of cool helper functions for select. Things like starts with, ends with, or contains that let you give it text inside of those, and it will keep or drop every column satisfying the search term you put inside of it. This is something I do a lot because I work with very large panel data sets sometimes. For instance, I manage at the University of Washington, I manage Seattle, I manage the Denver Youth Survey. At its current state, the Denver Youth Survey in its full format has 85,000 variables. 85,000 is a lot of variables, and because of the way the format's in, it's wide format. It has 1,526 rows, one for each individual in the survey, and then 85,000 rows, or columns, one for every measure. But it has things, it's a panel data set over time. So it has measures like this: married 10, 11, 12, meaning were you married in the year that you turned 10, 11, 12, 13, 14, so on and so forth. Well, maybe I want to get all of those variables that are married. I don't want to type out married 10, married 12, whatever like that. I don't want to type out manually. What I could say is I want to pipe my Denver Youth Survey into select, and then I want every variable that starts with married. It will give me all of the variables that start with married. It's case sensitive. It will give me exactly that. Or perhaps what I want is every variable that describes a person in the Denver Youth Survey in the year that they turned 18. I would say ends with 18, because the way I structure my data sets is the only thing in the data set that ends with the number 18 is the variables in the year that they turned 18. And every single variable that describes them in that year ends with 18. Uniform naming standards are really nice if you have a lot of variables and you want to be able to do quick selection like that. Okay, there's a lot of these. If you want more information on special things, you can do !select when dplyr is loaded. It will tell you a lot about it and link you to the other functions that you can use to do it. You can also do sequential selection of contiguous columns. So let's say you want maybe 20 variables that all occur in a row in a data set. You could do the name of the first one, colon the name of the last one, and it will run through all of them and get all of them using that kind of structure there. Start var, colon, end var. It's kind of the way that you might do a series of numbers in R, doing like 1 colon 10 will give you all the integers 1 to 10. It'll do it for variable names. It's kind of cool. Okay, so select is also used to rename columns, so that you could select a column from your data set and rename it at the same time. The syntax for this is the new variable name is on the left, the old variable name is on the right. So this would be saying, I want the Yugoslavia data, I want to select the life expectancy variable, but rename it life_expectancy. But if I do that, because of the way select works, right, it drops every variable I don't specifically select. So I do select, well yeah, I get life expectancy spelled the way I want it, but now I only have life expectancy. Okay, well this exact same syntax works in a function called rename. So I can specifically select variables like country, year, life expectancy, and then pipe it to rename. Rename has the same syntax. Life expectancy equals life exp, but it doesn't do any dropping or keeping of columns. But it has the exact same syntax. Very often I want to grab 3 or 4 variables, only those variables from a data set, and rename them all at the same time. I do it all in select. Other times I want to rename just a few variables because they have some particular wording, I want something different. Or maybe I want to be able to pipe them straight into a plot or table without renaming them, so I want to insert spaces into their names or something like that. I do that in rename, or in select, same time, whatever. Make sense? Cool beans. Okay, next, moving on to more fun stuff. Creating variables using dplyr. Okay, all variable creation in dplyr is done within the mutate function. It's kind of an oddly named function, mutate, but it encompasses a lot of different potential operations. If you want to make a new column in dplyr, it's always going to be in mutate. Okay, the way mutate works is we can give it any sort of mathematical formula, any sort of function operation that would change a column or generate a column, and we just say something like this. In this case, I'm taking my Yugoslavia data. I'm filtering down specifically to the country Serbia. I'm saying I want to select year, population, and life expectancy. Then I want to mutate. This says everything inside of that mutate call is going to be me creating new columns. You'll note here I can create multiple columns at the same time in a single mutate call, any number. I'm going to create 2 right now. I'm going to create a population in millions, which is equal to the population variable divided by a million, just a simple unit change, and life expectancy past 40, which is equal to the life expectancy minus 40. It's not how an actual demographer would do life expectancy past 40. I am angry at myself for putting that there, but that is how you could create a variable like this that is crude. Okay? So I pipe it to head. You'll see the original columns are still there. Population is there in life expectancy, but now added to it is pop million and life expectancy past 40, and it obeys the mathematical properties that we specified. Pop million is definitely population divided by a million. Life expectancy past 40 is definitely just subtracting 40 from life expectancy over there. Make sense? Any expression you want could occur on the right side of that assignment, and you just give it a new name there on the left. Yeah. We're going to get a little fancy with this over the rest of this lecture. Okay, so a common function you will use inside of mutate, and outside of mutate too for doing general sort of variable creation and stuff, is if-else. If-else will return a vector of values depending on some logical test. The way if-else works is you have a test first. Let's say it is x equals y. Anytime x does indeed equal y, this function will produce whatever I have in yes under there, whatever is the second argument in if-else. If that test, x equals y, is false, it will return the third argument, whatever is no there. If the result of that logical test is an NA, this function will return also an NA. Any failed test, the test that can return neither true nor false, returns an NA, and if-else will also in turn return an NA. It looks like something like this. This is an example, one where I have the numbers 1, 0, NA, which is not a number, and -2. If I run if-else on this and say my logical test is example greater than 0, so it's going to go down every element of example and test whether that one is greater than 0. So, and if it is greater than 0, it's going to return the word positive. If it is not greater than 0, it's going to return not positive. 1 is greater than 0, so it returns positive. 0 is not greater than 0, so it returns not positive. NA is not a valid thing to test, so it returns an NA, and -2 is not greater than 0, so it returns not positive. Very simple logical test. This is a way to convert a bunch of trues and falses. That test, example greater than 0, is just a bunch of trues, falses, and NAs. If-else converts those trues and falses into values. Okay. It's very useful. Okay. We can use if-else inside of mutate to create variables. It's very commonly used to create like binary variables for things, but we can also use it to create variables that have particular values or to change values inside of an existing variable. So here what I want to do is I want to create a new variable. I take Yugoslavia, I pipe it into mutate. I'm going to create a new variable called short country. I'm just going to create short country because I don't like saying Bosnia and Herzegovina every single time I see it. I want to say B and H because I am lazy. So we're going to say short country is equal to the result of this if-else statement. If-else is going to say if country is equal to Bosnia-Herzegovina, return B and H. If it is not, so if it is a false, just return country. So think about it. What is this going to do? Anytime it finds Bosnia and Herzegovina, B and H is going to pop out. Anytime it does not find it, it's going to give it the original value of country. So essentially, short country is going to be identical to the original country one, except for Bosnia and Herzegovina, in which case it's going to be a shortened version. So I see it spit out down here, head 3, B and H, where Bosnia and Herzegovina was, but then Croatia and Montenegro are untouched, right? And this is a nice way to structure this because we can read it like this. Read it, this text, as for each row. If country equals Bosnia and Herzegovina, make short country equal to B and H, otherwise make it equal to that row's value of country. I like to think of these things as a sentence, as a text, as a statement. If I write some code and I cannot explain like that line of code in a sentence, it needs to be broken up into more lines of code. This makes sense to me, but I've been doing this a long time. If this does not, break it out more, write comments, describe it to yourself. Okay.
Can we do multiple things in the if-else statement?
So if you want to do multiple if-else statements, not an if-else, but I'm glad you asked, because in 1 second I'm going to talk about how you do multiple if-else statements in dplyr. Okay, right.
Quick question. The as character, so it's already a character.
Yes.
But you still need the as character.
I'm doing that because I was worried when I wrote this probably, and this is the kind of thing I will do reflexively, I thought it might have been a factor and not a character variable, and I wanted to make sure it popped out as a character. It was in fact a character to begin with, so as character is not necessary. But sometimes type checking and type forcing, as somebody who spends a lot of time programming, I tend to enforce the types of data that come out of things, being like, I want to make sure it's character. Like that's what I was doing. I could have made it spit out as factor or something like that too if I wanted to, but in this case I did as character. In this case, it's unnecessary, but great catch.
So if you're sure that it's a character, for example, I could just write country?
Yes, absolutely. Yeah. And mutate is actually usually fairly smart, so it will tend to do coercion into the appropriate data type without even worrying about it. If you combine numeric and character stuff, it's going to come out as character, that kind of thing, without kicking an error. R in general does that. It's nothing specific to dplyr. If you combine multiple data types, it ends up as whatever is the the least structured data type. Nothing in R is less structured than strings than character data, so everything could eventually be coerced into a string. If you give character data to anything, it will become a string. That's the way it works. Does that make sense? Questions? Okay. Cool. So, let's say you want to do a bunch of if-else statements at the same time, and you don't want to write if-else, 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 if-else inside of each other, which is how you used to have to do it. There's a function in dplyr, my favorite dplyr function, called case-when. What case-when does is it will perform multiple sequential if-else operations at the same time. This will allow you to do things like create a new variable with values based on a bunch of different logical statements. This is really useful for creating like categorical or ordinal variables, or variables that are made up of a combination of other variables. So what I want to do here is I'm going to create an ordinal variable. I'm going to take my gapminder data, put it into mutate. I'm going to make a new variable called GDP per cap ordinal. That is going to be equal to case when and then a bunch of statements. This is how it's going to work. It's going to run down these statements in order until it finds a true. And then it's going to assign whatever is the first thing that is a true. What it's going to do is first it's going to look at GDP per capita and see whether it is below 700. If GDP per capita is below $700, it is going to assign to it the word low. Then, if that is not true, if it's false, or if it's NA, actually if it's NA, it's going to give you a warning. If you have NA is going to case when, make a is.na statement at the top and assign NA to it or something like that. Case when does type checking. Anyway, next, GDP per capita greater than or equal to 700 and less than 800. So if it's anywhere in that 700 to 800 gap, I'm going to say this is a moderate GDP country. If that is not true, because I know I don't have any missing data or weird values, I want everything else to be a high income country, because everything that remains must be greater than 800. So I just say true equals high. Well, that just means that the first time it encounters a true, it assigns that value. Well, true is definitely going to give it a true, so I can assign high to it. Then I pull out some values just to show you. You can see Afghanistan from 1977 to 1992 went from being a moderate income, high income, back to low income country within that period of time according to this variable. Neat, right? You can do an arbitrary number of these like statements, and you don't even have to use the same variable in all of them. I could say I want this country to have this value if GDP per capita is above this or population is below this. I can do all kinds of stuff like that. Multiple conditions inside of it. It's a wonderful function. Questions?
I have a quick question. Will it, if you can you do like greater than 7? Does it kick it out, such that you don't need to necessarily bound your conditional? So can you say something like greater than 700, then greater than 800, greater than 900? I guess you do that in reverse. Greater than 900, greater than 800, greater than 700, and it'll just.
Yep, because it does them in order. So yeah,
so
you don't have to make specific bounds.
Okay.
Yeah, as long as it would be correctly assigned, running through them sequentially, it will come out the way you expect.
Okay.
That's kind of the interesting thing about case when is it's not a simultaneous evaluation, it's a sequential evaluation. So 1, 2, 3, 4, 5, 6, so. So for that, it'll work absolutely. I tend to like to be specific like that, but it is unnecessary. I could easily, for that other statement down there, I could have just put GDP per cap less than 800, and I would have gotten the exact same result for the second value.
Can I put multiple conditions in case when?
Oh, yes.
Okay.
So when you say
Multiple conditions meaning with multiple variables. GDP per cap is less than this, life expect and life
and or
life expectancy.
Yep, you can
something.
chain as many as you want. You could have basically anything that its final evaluation, so any like whole sentence of conditions, as long as the final thing that comes out is a single true or false, it will work. So that means any set of and or statements will always produce a single true or false. It will work in case when. You could do very complex. You could also, inside of there, you could write your own function that does some kind of complex work on a particular variable to produce a single true and false. So it doesn't even have to be like a normal logical condition, and it will work and it will do it. Yeah.
If you didn't do an ending one,
Mhm.
that true was high, what would happen? Like if.
You'd probably get NAs.
Okay.
Yeah, it would get to the end and kick NAs, or it might kick a warning.
So you do have to end it out, you can't just.
Yeah. Well, I mean, you don't.
Yeah.
If you're okay with NAs, that's probably fine. But I think it will actually kick a warning and say, I don't know how to categorize this value. Yeah. So normally you do want to finish it off, and normally, you know, if you want something to be an NA, I usually know what it is that I want to generate an NA. I put NA assignment first, usually in case whens. Because if something's an NA going in, it's going to break any one of those logical statements. And if one of those logical statements evaluates to an NA, case one will return an error. So you have to make sure to take care of NAs first. But you could make something produce NAs and it would be perfectly happy with it. Yeah. Okay. Cool beans. Okay. So that's everything I have to say about creating variables in dplyr. A lot of tools right there. There are a lot of other things you could use to create variables in it. I recommend looking like online, tutorials, data camp, all these kinds of things. Links off of my website, so on. But we're going to move on to new and exciting territory. So we're going to move on to summarizing data. So dplyr has a function for general aggregation of data called summarize. What summarize does is it will take the columns of your data and it will compute something across those columns, like down the run of the column, using every single row that you give it. You might want to do something basic like count how many rows there are. Let's just get a sample size, right? Calculate the mean of a row or multiple rows. Compute the sum of a row or multiple rows. Maybe obtain its minimum or its maximum value. Inside of summarize, it works like mutate, but you can only use functions to generate a variable inside summarize that will take multiple values and return a single value. Things like standard deviation, mean, max, min, first, last. Those will return a single value. They will work inside of summarize. Let's get some examples. So, let's say for the year 1992, I want to get, or 1982, I want to get the number of observations, the total population, the mean life expectancy, and the range of life expectancy, specifically for former Yugoslavian countries. I take my Yugoslavia data I created a while back. I filter down to 1982, then I pipe it into summarize, and I say the number of observations is going to be equal to n. N is a function that gets the number of rows in a data frame. I would say total population is going to be equal to the sum of pop. So that's going to take all the values in the population column, add them together. Then I say mean life expectancy is going to be the average life expectancy, the mean, and then the range of life expectancy is going to be the maximum of life expectancy minus the min of life expectancy. What comes out from summarize is a single row of data, because it's taken every row of the data I've given it, run these summary things, and reduced it to a single row of data where each output has a single value. So I know that the data I gave it, which is five former Yugoslavian countries, year 1982, there are 5 observations. So it says 5 observations. This was the total population of the former Yugoslavian countries in 1982. That was their mean life expectancy, and the range of life expectancy from the highest to the lowest was 3.94 years. So not a big life expectancy between these different countries. So these were calculated using every row in Yugoslavia. This is how you do quick summary statistics. Make sense? Okay. So, if you want to do lots of different summaries, like let's say you want to do the same summary, maybe I want to get the means and the standard deviations of every variable in a data set that has 100 different variables. I just want to see them all really quickly. There's a function called summarize at, and related functions I'm going to talk about in a second, called summarize all and summarize if, that I just can put a list of all the variables I want and a list of the functions I want to call, and then it will call that summary function, like in this case mean and standard deviation, for each one of those variables, and just go across all the variables I do it. So in this case, what I said is I want Yugoslavia, 1982. I want to summarize the variables, life expectancy and population, and I want to, for each of those variables, get their mean and their standard deviation. What pops out, it does the naming for you, is life expectancy's mean, population's mean, life expectancy's standard deviation, and population standard deviation. Inside of that vars command up there at summarize at, I could have used any kind of like helper function that the select function will allow. Let's say I had that data set with all of the marriage variables. I could have just said starts with married, and it would have given me the summary statistics, the mean and the standard deviation for every one of those married variables. Okay, so this is a way to do quick multiple summaries if you don't want to name every single individual one out like we did up here. This will just automatically name them and do them.
So summarize at needs the grammar of the variables and then the function.
Yes. Yep. Yeah, that's its particular syntax. Let's say you wanted to do every single, you wanted to get the mean and SD of every single column in a data set. You could just use this function here, summarize all. Summarize all says every variable that gets sent to it, I want to run this summary statistic on. So then you just give it the functions. This would be saying mean and standard deviation. Then it would get the mean and SD of every variable in a data set. Keep in mind that sometimes you'll have variables for which a mean or a standard deviation can't be calculated, categorical data and stuff. They will kick an error. Let's say you want to summarize then only the numeric variables in a data set. You could use summarize if. Summarize if takes a logical statement, but it runs that logical statement on the columns. For instance, is.numeric. Anytime then this function encounters a column which contains numeric data and only numeric data, it will get its mean and its standard deviation. So there's a lot of powerful functions here for data summarization that make it quite trivial, including basically searching for the appropriate columns to run stuff on. Okay. Not going to go into these too much. They basically take the stuff that we covered in mutate and summarize and generalize it to many columns at the same time. Okay. Now, we saw before that everything we did with summarize would just take the entire data frame and produce a single row. Well, often what we actually want to do is we want to do summaries within groups of units, right? We don't want to just take this entire data frame that has all these different countries. Maybe instead what we want is we want to take all of the different years of data within each country, but get a summary for each country, or across every country and get a summary within each year. We can do this very easily. There's a special function in dplyr called group by. The way group by works is you do a call to group by with some variable you want to group on, and then every subsequent function after group by will be performed within each group instead of across the entire data set. So any function we call after group by gets computed inside of that. Normally what we're going to do is we're going to group on some variable that is, say, integers, some kind of factor or categorical data, character values. We usually are not going to group on continuous real values because, right, you only have a single element in each group. Occasionally there's a reason to do so, but mostly it's going to be like integers, factors, characters. So here's an example. Let's take former Yugoslavia again. I'm going to group by year. Within years, I want to summarize the number of countries, which is the number of distinct countries shown in each year, and distinct counts how many individual values for that variable there are and just returns the integer number. I want the total population, so the sum population, and the total GDP per capita, which I'm going to do as the sum of population times GDP per capita divided by the total population. Notice I'm using a variable divided by total population I calculated on the previous line inside of the same summarize call. The way summarize works is it calculates these variables sequentially within summarize, so you can refer to a variable you just created inside of the same summarize call. Kinda neat. Saves you from writing summarize again. dplyr is good for lazy people who don't like typing, or who are bad at typing like me. I make a lot of typos. Okay, I pipe this into head 5. Now what we get, even though we summarize, we now have one row for each group that we gave to summarize. So our former Yugoslavia had a whole bunch of different years. I'm showing the first 5. So now we have one observation for each year. So year 1952, within that there are 5 different countries whose data are combined. This is the total population of all 5 countries put together, and the GDP per capita on average for all 5 countries put together. So now we've summarized all of our data down to a year unit. Well, this is how you convert your unit of analysis before some kind of statistical routine. Maybe you have a whole bunch of country data, but you're interested in looking at continents. You just say group by continent and summarize across these different things. Now your data set is in continent level. This is how we work with and convert panel data and things between different formats. It is trivial. Right? Makes sense? Any questions?
And distinct is just the number of distinct
Values. Yep. Yeah. Don't use that one too much, but sometimes you just want to know that. That'd be actually a good check to put in there to make sure that a country didn't somehow disappear when it's not supposed to. Sometimes I'll include check variables like that as I go along, often without even thinking about it. So yeah, good to point that out. Yeah. Yeah, there's a lot of those odd little functions built in dplyr. Like if you do question mark like mutate or something, go into dplyr, but then look at the full list of dplyr functions. dplyr has like 200 functions built into it for doing specific little things inside of it. It's a great package. And the associated packages are similar, just amazing. There's just a wealth of stuff. I couldn't possibly lecture on probably half a dplyr in a day. Okay, so grouping can be used in combination with functions like mutate or filter to do things like generate rank orders within a group, lagged values, cumulative sums. If you're interested in these, which are called window functions, things that operate within a window or a group of something, there's a vignette there that you can go to that talks about how to work with these different window functions. Here's an example of one. I go Yugoslavia, select down to the variables country, year, and population. I want only years greater than 2002. I group then by country, and I want to generate a lag population. So that is the lag of population, so the previous year's population. So this order by automatically makes sure the data is ordered by year for this calculation. Then it just returns the previous year's population. And then the population change is going to be equal to pop, this year's population, minus last year's population. But because I did group by first, it does these calculations within the individual groups, which were the countries, right? So Bosnia and Herzegovina 2002, Bosnia and Herzegovina 2007. There's a population change and a lag pop for the second observation. There isn't one for the first observation because there's nothing before 2002. I filtered it out for it to calculate. But this is how we get, say, like a lagged variable within individual units. So say we have, 20 observations of Bosnia and Herzegovina, we'll get 19 lag populations for that. But obviously, you don't want it to go to, like for the Croatia line, go back and get the population for Bosnia and Herzegovina. This takes care of that separation out in the kind of grouped calculation of things. It's very easy. Okay. Okay, so we're chugging along, tidying data. When do we go to? Stuck your eyes.
2, and then we have the room till 2:30.
Oh, we are great then. We're on target. Okay, tidying data. So, let's say you've loaded in a new data set that has real data. Those gap miter data I'm working with do not look like real people data. They're all clean and pretty. The values make sense, all that kind of stuff. Real data we encounter never looks like that. God knows. So, let's say you load in a new data set. These are what I say are sort of the first things you want to check into before we do any real operations on a data set. Things like, did the last rows and columns from the original file make it in? And I say the last rows. It's usually really obvious when the first rows and the first columns of something don't come in right. We often forget to check the last rows and the last columns. Commonly we'll read like a data set or something in, and for some reason it will just chop off the last 100 rows or the last bunch of columns due to some kind of formatting thing. Often we're reading from Excel sheets, and God only knows what kind of weird stuff people have done to an Excel sheet. People store useful information in Excel sheets using colors and formatting like bold and italics. Don't do that. That just gets lost as soon as you convert the format. Sometimes when people do that kind of stuff, things just don't come in. Make sure they come in right. Next. Are the column names in good shapes? So if you're doing something like you're reading something in from a CSV or something, I'm not going to go into all the different data reading in today, but you might just want to, as you read them in, make sure the column names are either manually assigned or they come in a logical format, or once it has come in, you look at it and you're like, oh God, these names are horrible. You could just use rename to change them. Very often I will actually, in the read_read.csv, I'll just change the column names as they're coming in manually because they're going to come in bad. But I don't want to change them in the actual spreadsheet because I like to pull the spreadsheets directly from the source that's generating them or something. Yeah, you don't want to manually change anything in an Excel sheet. Just take it to whatever format they give it and change it in R. It's nice. Okay. Or this is a really common one if you work with Excel sheets. Are there decorative blank rows or columns to remove? So the Tidyverse does have functions for reading in like Excel sheets and things. So there's read_CSV for CSVs, and there's a whole package called read Excel for dealing with this in Excel sheets. Those ones have arguments you can give the read-in that say ignore these rows, and you can number them off and stuff like that. So you can just ignore these decorative rows. This is really common, even government data. There's a lot of like government, Bureau of Labor Statistics, even census stuff, God knows the FBI stuff that I work with. It all comes in with bizarre decorative rows. Well, you want to be able to chop them out, but you want to be able to do them kind of programmatically. You don't want to have to like manually, every single sheet you get, you don't have to go and open the sheet and check it. There's ways to do this. Not going to go too much into today, but you can use filter or select to get the appropriate rows and columns after it's in, or before it's in, you can do modifications to read_CSV. So, a really important thing is immediately recognizing how missing values are being represented in the data. R by default uses NA for every type of missing value, but different statistical packages, different people use different values, right? Blanks are relatively common, periods are sort of a status style thing and are pretty common. SPSS and stuff, you commonly will see things like 999s, things like that. Every data set has its own missings. One of the first things I want to check is figure out how they're formatted. I'll scan through it and look for values. One of the easy ways to find missing values is you look at a column with continuous values, tabulate it, but then select only the values that exist more than like 5 times. If it's a continuous thing, you're usually not going to see the same value a whole bunch of times, but then you'll see like 10,000 99999s. There's your missing values, right? Okay. You could modify those missing values to be whatever you want them to be. Even in R, sometimes I use numeric indicators. Sometimes I have like 5 different very specific types of missing, different types of sensoring, like panel data. I want to have indicators. I usually will have an entire own like column. Sometimes like every variable in the data set will have a second column. Whenever an NA exists, that will have a character entry that says what type of missing it is. It's a good thing to do because, you know, it's like, oh, it's censored because they never had to answer that survey question. Maybe it's missing because the person's there. Maybe it was a refused to answer, which I don't want to treat the same as they weren't there to answer it, blah, blah, blah. But when those NAs load, God only knows what format they're come in, I want to recognize all of them and immediately change them to NAs or convert them to a new value telling me the type of missing it is. Okay. Then another one, are there character data? Zip codes look numeric to people, but they are character data. Are they being incorrectly represented as numeric data? So if you load in a CSV sheet with zip codes, any zip code with a leading 0, it's going to probably chop off that 0 because it thinks it's numeric. That 0 is informative. You want it there, it's a string. You can either tell it to load in as a string with column types, which I'm going to show us an example of in a bit, or add it back on at the end. Zip codes are the one that drive me the most nuts for coming to when they shouldn't, but other things sometimes come in. IDs of individuals in a panel survey, very common, right? We all know this. Okay, so once we get past all those spot checks, let's say some data comes in. You have some data like this. This is actually a real tabulation of students, I think, from a particular class I had. So this is a normal table you might see. As a column for the program, number of female, number of male students in 4 different schools. So the Evans School, the Arts and Sciences, School of Public Health, and then other. So in this particular case, an observation in this data is a group of students from a program of a given gender. The variables represented in this table are the program, the gender, and the count of individuals. The variables are not program, male, and female. The variables are gender. The values are, for program, Evans School, Arts and Sciences, Public Health. Gender, its values are male and female, but they're being represented up in the column headings instead of being in the actual cells, and the count is being spread over 2 columns. This is something I would call as slightly messy data. It's very human readable. It's a crosstab. Anybody can read it, so it's nice. For your computer, this is not a useless format, but it's still annoying to deal with. An ideal format for a computer, and especially in the Tidyverse, is what is referred to as long data. In long data, every variable is a column. Any variable is not, their variables are always a column. They're not a row, they're not stored in rows. Each observation is always a row. Observations are not spread across multiple rows. Something like this would be ready to throw into any kind of statistical model in R, or throw into like a ggplot, which I think I'll be doing a workshop on visualization next term maybe. We'll see. Yeah, this is the kind of format we want our actual data in. So we know Evans School, female students, there were 10, Evans School male students, there's 6, so on. This is tidy format. I'm going to talk about this more in a second. Okay, so Here I'm going to bring in truly hideous data. Data that were not meant for, okay, technically they're meant for human consumption, but it is a horrible thing to look upon. So, these are the Billboard Hot 100 for the year 2000. You can load it in directly from Hadley Wickham's GitHub, which I do here. I just pull it down here. I'm not going to explain what's going on here. This is basically me manually specifying the column types because it's a CSV sheet. It doesn't have any metadata telling you what the types of data should be. You have to specify it for some of the columns that have lots of missings. That's all I'm doing. For information, click there to link to the lecture where I go into way too much detail on that. All the slides here, of course, are pulled from a combination of my lectures and some added content. Usually, if you want more detail on anything I talk about, I can send you a link to the lecture. Okay, which is accompanied by a video too, so you get to listen to the dulcet tones of Chuck. Okay. Now, Billboard is ugly messy. So, it looks like this. We have a year column, which is it's of the year 2000, so the year column to begin with is already useless. It has an artist, the particular track, the length of the track, the date it entered the Billboard Hot 100, and then afterwards, week 1, week 2, week 3, week 4, week 5. This is its ranking, its location on the Billboard Top 100 in that week after the date it entered the Billboard Top 100. So week 1 is a different week of the year for every single song up here because it entered at a completely different time. And then there is one column for each week up to week 76 because some songs began before the year 2000 on here and trended there, and some in here went all the way past the end of the year 2000, but because they were in the Billboard Top 100 in any time in the year 2000, they go. So they can be on it for up to 76 weeks. Working with data with 76 columns of something you care about is a nightmare, right? And more importantly, every single one of those columns is actually the exact same measure. It's the same variable spread across 76 columns. This is a terrible format. Okay. So, the observations in the data are the week since entering Billboard Hot 100 per song. The actual observations are those weeks since entering. The variables in the data are things like, year, artist, track, song length, the date it entered it, the week since it first entered the Hot 100, and its rank during the week. The last two are spread over tons of different columns. Okay? The values in the data are things like, the year 2000, 3 Doors Down, Kryptonite, the length of that song, the date entered, week 3, rank 68, right? There's a lot of useful data in here, just spread all over the place, and it's gibberish, honestly. So, tidy data, again, tidy data or long data are data where the values for a single observation are in their own row. If we remember those Billboard data, an observation is a week since entering the top 100. So that means there should be one row per week for each song. The values for a single variable are in their own column. So there should only be one column for rank in the entire data set. The observations are all of the same nature. That meaning every single observation should be a top 100 week observation of a song, right? You don't want to mix and match units. In this case, it's hard to mix and match units, but sometimes you get data sets where a row is actually like a descriptor for an entire country, and then within it is like subunits of the country. That doesn't make any sense. Those are different units of different like types. You either want to aggregate all of the same type or get rid of those things and split them out of the data set. Okay? Next, why do we want tidy data? So the question is, why do I want to coerce it into this very particular format? One, it's a lot easier to understand many rows than many columns. We're much more used to reading tall things than really wide things. Just using on your screen, trying to scroll left to right across columns, it's annoying, it's unintuitive, we hate it. It's just the way we're socialized to it. I'm sure if they decided to do displays going left to right, more commonly back in the 60s, 70s when they started really standardizing stuff, maybe we'd be used to going left to right. Probably not, but what do I know? Next, tidy data is required for plotting in ggplot2. For people who do a lot of visualization in R, you're probably using ggplot. It expects long data. Next, most statistical procedures in R, basic like linear models, GLMs, hierarchical models, mixed effects models of any kind, they all expect long data. The only commonly used thing I can think of that expects wide data is structural equation modeling. That's about it. It's about the only time I spend a lot of time in wide data. I do a lot of SEM, so I spend a lot of time in wide data. But it's easy to move between wide and long data, so it's no big deal. Okay, fewer confusing variable names. If you only have 10 variables, it's a lot harder to have confusing variable names. If you have, like some of my data, 85,000 columns, it's hard to keep them all unambiguous. Luckily, R can have arbitrarily long variable names, so sometimes you'll have sentence-length variable names. I don't like it, but sometimes you need it. Yeah, and then fewer issues with missing values and imbalanced repeated measures data. Because every observation, like every person hour of observation, person year, whatever, is its own row, it's unambiguous when there's a missing value for a particular thing. That person hour has a missing value for that one column there. When things are spread very wide, missing values get weird, gets hard to track them down. Okay. So, the tidyr package inside of the Tidyverse has functions used to tidy up data. And by tidy up, I mean get it into this tidy format. It does things similar to reshape in Stata or vars to cases in SPSS. Pretty much every package or anything that can deal with converting data in formats has some different ways to go from wide to long and things like that. So the key functions in tidyr, in particular, is gather. What gather does is it will take a particular set of columns you give it and rotate them down. So if you have a whole bunch of columns going like this, it rotates them down to make 2 new columns. If you gave it 100 columns, it still produces 2 columns. What it does is it takes all of those ones, all the values in them, it generates a key and value pair. The key is going to be the name of whatever column was originally there, and the value is whatever value was in that individual column. It rotates them down. So like, let's say we have week 1 to week 76, columns with ranks in each cell under those, it's going to rotate them down. So now we have week 1, week 2, week 3, week 4, week 5, and then the value for week 1, week 2, week 3, week 4, week 5. A key and a value pair. Actually, sorry, key and a value. You people are facing this way. Okay, yes. Okay, we'll have lots of examples of this. It's harder to explain than it is to show. Spread is the opposite of gather. Spread will take 2 columns and rotate them up into an arbitrary number of columns depending on how many values there are for the key. Don't do spread a lot. Normally we want to get things into long data, but sometimes, and I'll show an example, we want to spread out something that is actually meant to be in wide format, but we're currently looking at it in long. It's good for generating tables and crosstabs. We'll show in a minute. Then there is separate. Separate will take 1 column and pull it apart into multiple columns. This is really common. Say you've gathered a bunch of data, but there were values embedded in the column names. For instance, week 1, week 2, week 3, we might want to separate that out because the number of it is some useful information and we just want that number. If, for instance, you only want to extract a number and you don't also need some text out of there, extract numeric is a shortcut for cutting up a column and pulling out only the numbers that exist in it. Really convenient for when you want to rotate a bunch of columns like married 10 through 80. You rotate them down, you just want the numeric component. Extract numeric will pull that out for you. There's also one I don't use a lot, but people do find useful if they work with a lot of wide data. Extract will spread a column into multiple sets of columns. So let's say you have a very large, wide data set like that Denver use survey I talked about. If I gather that and I gather all 85,000 columns, I have a single row that does have all the numeric, all the text values for everything in that data set. But if I want to spread it back out, I want to spread it back out into sets of columns. I want 1 column for married, 1 column for employed, 1 column for incarcerated, that kind of thing. Extract will allow you to, instead of rotating them all back up, it will let you rotate them in sections back up into their own columns. It's very complex to explain. Hadley Wickham has a Stack Overflow response to somebody asking how to use it that has a great illustration of how to do it in a weird case, but you can basically look for the information on extract and see how to use it. If you need to work with data in wide formats, say structural equation modeling, mastering the extract function is really useful. There's also another old package called Reshape 2, also made by Hadley Wickham, that has melt and cast, which is made for going from wide to long data, but it's been mostly replaced by tidyr. The syntax is very elegant for tidyr, but the first few times you look at it, you're like, I have no idea how this works. That's okay. Beat your face against it, and eventually you'll figure it out. It worked for me, it works for most people. I have a lot of students, they all eventually figure it out. Okay, so how does gather work? What I want to use here is I want to take gather to get the week and the rank variables out of their current layout and put them into 2 columns. This is going to result in a very large increase in the number of rows and a very large drop in the number of columns. The way it works is really easy. I load up my tidyr package. I say Billboard 2000 is going to be my original Billboard 2000 raw data. Then I say gather. Key equals week. This says I'm going to generate a new column called week, which is my key column. The value is rank. It's going to generate a new column called rank, which is going to contain those values. And then I want to gather every column that starts with WK. There are 76 columns that begin with WK. What it's going to do is it's going to take all of those columns, every value in every one of those cells, and it's going to basically stack them and assign their column name for that column as the key over on this side. It's going to convert 76 columns into 2, and it's going to take this Billboard Top 100 and go to a really long format. Before we had like 81 columns of data. We now have, I see dimensions here, 7 columns of data. That's the second value on dimension. But now we have 24,092 rows. Okay? This is what our data look like now. Year, artist, the track, its time, the date it entered, what week it is, and then the rank it was in that particular week. Well, this is exactly what I wanted. There's each song for every week it was on the Billboard Top 100, it's got its own row, and it has a rank associated with it. I could have sorted by, I could have shown one song and shown how each song, if the song was on for 10 weeks, it would have 10 observations in this data set, right? Anything else I want to mention? Yeah, okay. We've got a single week column. It is not perfect, however. So if I get a summary of the rank here for it, the thing is it rotated it down, but not every single song was on the Billboard Top 100 for 76 weeks. In fact, the vast majority of them were not. By default, it will still create a row for all those observations that are missing. It created 76 rows for every single song, regardless of how many weeks it was on the Billboard Top 100. So if I get summary of its rank, Billboard 2000 $ rank, minimum rank is 1. You can't be better than number 1 on the Billboard Top 100. Maximum is 100. You can't be worse than the top 100. But it has 18,785 NAs for the rank. There's only 24,092 observations. The majority of them are NAs because most songs only spend a little bit of time on the Billboard Top 100, right? Okay, so this format is an improvement, but we don't want all those missing observations. We just don't care about them. They weren't on the Billboard Top 100, so why are they even in the data at that time? What we can do is we can add an argument to gather. Billboard 2000 raw, type it into the exact same command I did before, but then I say na.rm equals true. This says that if I spread these things out, if the unit that I am spreading out, which is going to be the one measure, whatever we care about in this new long data set, if it is an NA, just drop the row, because it conveys no information. It's a missing, there's nothing there. Now, if I do summary of Billboard rank, minimum 100, minimum 1, maximum 100, there's no NAs. We just dropped all those NAs. There's a lot fewer observations. So you can do it all within that little gather framework. Now think about if you encounter a data set that looks like that. It's a mess. It has all those columns. The idea that you could get it into essentially your desired format with one line of code is very nice. Turns out this works almost all the time for me. I'll get hideous data with bizarre measures like that. I can usually do it with one gather call. It's pretty amazing. Yes?
One question. Can you go to slide 42? I think it was on slide 42. Maybe, sorry, the next one. There was a argument called DLM billboard or something. So what was that doing?
Is what now?
There was a DLM billboard. I'm not, maybe it was 41, I'm sorry.
Oh.
Yeah, that dim, sorry, dim.
Oh, dim Billboard 2000?
Yeah, what is that?
Dim is dimensions. So dim is a quick function that tells you how many rows and columns a data frame
That's
has.
what it's telling me there.
Yeah,
Okay.
yeah, dim. Dim does something different depending on what object you give it, because some objects have multiple types of dimensions. Like if you give it a multi-dimensional array, it will give you one entry for the dimensions in every single dimension of it. You know, if an array has like 5 dimensions, you'll get 5 values. Dim doesn't work on vectors though. It will kick an error because vectors have 1 dimension and you apparently can't get dimensions of a 1-dimensional thing in R. It's a quick way just to know how many rows and columns there are. Yeah. Okay. Done that. So, in this Billboard Top 100, the column, do I have a good one? The column for the time, the length of the song, is really readable to human beings. For column 22 is unambiguous to us. It is 4 minutes and 22 seconds long. To a computer, that is text. That is nothing, that is gibberish. It is useless to a computer because it can't just be like, easily be like, oh, that's 4 minutes and 22 seconds. It prefers numbers, decimals, and things. So maybe we want to work with that column. Separate is an easy way to quickly extract information from a particular column that is maybe multiple pieces of information with some clear divider. In this case, what I want to do is I want to take my Billboard 2000 data, I want to separate that time column into its minutes and its seconds, right? The minutes is everything that occurs before the colon. So I say separator equals colon. What I'm separating into is the minutes and seconds. That's going to create 2 new columns, one called minutes, one called seconds, separated by this colon. So if the value is 422, in the first column, minutes, it's going to put a 4. In the second column, after the colon, it's going to put the 22. Okay? Convert equals true says, okay, it's text right now. If it's possible to make it numeric, convert it to numeric. Automatically does it. Then I immediately say, okay, I don't care about the minutes and the seconds. I care about the total length of the song in minutes as a decimal. So I say I'm going to mutate. The length of the song is going to be the minutes plus the seconds divided by 60. So this is going to be minutes in decimal form. Then I immediately say select minus minutes minus seconds. I'll go right ahead and I drop the minutes and seconds columns I created, keeping only the length column I generated. I then get a summary of it, and we see now the Billboard Top 100 of this entire span. The shortest song was 2.6 minutes, and somebody went Freebird nuts at 7.833 some point within the year 2000. Okay, makes sense? We've taken something that was text, might have been annoying to convert. We just say, nah, it's actually 2 columns. It's a minutes column, a seconds column. We'll spread it apart, gather those data back together, put it together. Lots of operations in a very small space, but it's easy. Okay, parse number. So sometimes what we want in a column, we know it has some text and it has some numeric data for each value. We don't care about the text, we just want the numeric data. In this particular case, week, all those week columns drop down, and now they say things like week 1, week 2, week 3, week 4. Well, that column, the top of it is already, it says week. We know it's a week. We would like it in numeric form. I can use this function, parse number. So I take my Billboard 2000 data, I pipe in a mutate, I'm going to replace the week column. So in mutate, if you want to replace a column, just write a new column with the same name. It overwrites that column. R works this way in general. So I say, new column week is going to be equal to parse number week. What this is going to do is it's going to go to every entry in that entire column, and it's going to just pull out whatever numeric information there is and discard the rest, and automatically convert it into a numeric column. Okay? So now if I get summary on Billboard week, it's now numeric data. It has a minimum and a maximum. There's no minimum and a maximum to week 1, week 2, but number 1, number 2, so on, is numeric. So now we see the minimum was week 1, the maximum was actually week 65. So this also tells us another thing. Those 76 columns we had originally didn't actually go up to week 76. It was missing for everybody on those later columns. Okay. If you need to do more sophisticated conversion or pattern checking, I like this. I left this in from my slides from my class. You'll need to use string parsing, covered in week 8. I don't think we're going to be here for 8 weeks. But that does tell you where to look in my lectures if you go to my website. Week 8 is entirely on handling text data, string parsing, regular expressions. Make the students go learn regular expressions in my class, which you're just like, oh my god, this is so hard. Then at the end of it, they're like, this is the most powerful thing I've ever seen. Regular expressions is a generic logical language for parsing text and returning like true-false statements and extracting things. If you work with much text data, it is absolutely worth it to start learning regular expressions. You can do things that are literally impossible without regular expressions. It's amazing. I have a whole lecture on it. Okay, so spread. Spread is the inversion of gather. Okay? So gather is for taking a whole bunch of columns and converting them into 2 columns. This is for taking 2 columns and converting it into a bunch of columns. This is common if you have something like this. Let's say we have data that looks like this. We have groups, we have a statistic, and we have a value. So for group A, its mean is 1.28, its median is 1, its ST is 0.72. Okay? This is a kind of thing where we might get a table that looks like this, but this is not human readable. This is very easily machine readable. You could plot these statistics like this if you want nicely. But for us, we probably want mean, median, and SD in their own columns, right? It's super easy. So I generated the data. So this is here, I actually just generate the data like right up here. And then I say, let's spread it. So if you're curious how I generate a table like that, you can look through that code. I'm not going to dwell on it. So what I'm going to do here is I'm going to take my too long data that I had before, and I just say spread, the key equals statistic, and the value equals value. You'll see back here, the column names were statistic and value. Spread is the opposite of gather. In spread, you actually give it the two columns you want to spread out, whereas in gather, you give it names and it makes those two columns, right? So in this case, it's destroying the column statistic and value and replacing new column names made from the contents of the key column. And the numbers that go in it are the values. Okay, now this is group A's mean, median, and SD, and group B's mean, median, and SD. So convenient for flipping between tables. Maybe you had a whole table of like coefficients of something. You might want to look at them in a format like this, where each group's like coefficient, or each like subsamples is across this, but to plot it in something like ggplot, you'd want to flip it down to that long format. You can just gather and spread and move between formats. The nice thing is tidy data is highly amorphous. You can easily move it in any format you want, like trivially just convert it all kinds of things, once it's in this kind of clean original format. This is one of the real powers of it, is like, if somebody's like, well, I need these white data for something, one line of code will convert into whatever format they want. As long as you've stored it in this kind of molten format of really long data. Okay, so some data prep here. Okay, so let's imagine that what we're interested in is we want to look at the songs that hit #1 on the Billboard Top 100, and we want to see how they got there versus the songs that did not reach the top 100. I could, say, calculate the best rank that any song hit on the Billboard Top 100 like this. I say Billboard 2000, I'm going to group by the artist and the track. I'm doing this because I want to look within each song, but each song for each artist has many different rows. So I want to look within and I want to see when that particular song hit its best possible time at the Billboard Top 100. So I'm going to say summarize. Summarize, its minimum rank equals the minimum of rank. So the best possible rank is 1, which is the lowest rank score. So I say minimum. If that minimum equals 1, I want to say that week it was at rank 1. So the second thing I'm doing is weeks at #1 is equal to the sum of this logical condition, rank equals 1. Rank equals 1 will take a value of true every time it encounters a row that is rank 1. Well, trues and falses are 1s and 0s in a computer, so if I summarize and sum the number of trues, it's going to add up all of the trues, all the times it was rank 1. Anytime it was not rank 1, it doesn't add anything to it. So that will generate a value for the number of weeks it was at the best possible score on the Billboard Top 100. Then I'm going to mutate a new variable called peak rank. If else the minimum rank was 1, it hit #1, otherwise it didn't hit #1. I don't actually end up using the number of weeks at #1, but I generated it because I'm like, oh, I'm already there, maybe I'll use it later. Okay. Then what I do is I've done that, I merge it back onto the original data. I say Billboard 2000, left join. I'm going to cover joins in a minute. Left join back here. Left join just says best rank is a data frame that has unique artists and tracks. I want to match those data back on by the artist and the track. That's all it does. That's how you merge data. We're going to go into it in detail if I have time in a bit. Okay. So now we have a data frame that is the original data frame, but now added to it is this information on its minimum rank, its peak rank, all that kind of stuff. Okay, so I can see which songs were #1 for the most weeks. Billboard 2000, I select, I'm only interested in the artist, what track it was, and the weeks at #1. That's still going to be a lot of rows. So each song is going to have however many rows it was on the Billboard Top 100. So I say, okay, I only care about the unique observations because I'm only looking at the number of weeks it was at #1. I say distinct artist, track, and weeks at 1. That will keep only the rows where all 3 values are jointly unique. So if something, in this particular case, let's say there were 10 different observations of Madonna's music, it's going to cut it down to 1 observation because for every one of those observations it had the same number of weeks at #1, it had the same artist, it had the same song name. Distinct gets the unique rows for some combination of variables. So now we see here, I arrange descending weeks number 1 because I want to start at the highest value of that. What song was on the Billboard Top 100 number 1 for the most weeks? And then I get head. Destiny's Child was killing it in the year 2000, followed by Santana, just making on the list, and the whole reason I did head 7 was so that I could get Enrique on the list with Be With You, number 3. Okay, so we've gotten some useful information if you really care about the Billboard Top 100 songs of the 2000, like some of us. Okay. I'm going to do a little bit more with these at the end if we have a little bit of time. Okay. Another thing we might want to do is get usable dates. So right now, we have like, it's not shown here, but we have the date it entered. We might want to know what is the date in each week going on. So instead of it being like week 1, week 2, week 3, we want to actually have the week it was in. So it's like, I want to know, oh, the second week for this song was the first week of November. For this particular song, its second week was the second week of March or something like that. What I do here is I say my Billboard 2000 data, mutate. The date is going to be date.entered plus the current week minus 1 times 7. It is a date object. Date objects are numeric, but their units are in days. So if I want to add a week to it, I just multiply the week minus 1 because it starts in week 1. So if I want to see 7 days later, what score it was in its second week or what date it was in, week minus 1 is add 1 week times 7 adds 7 days. That's 7 days after the date that it entered. Okay? Billboard 2000, I arrange by artist, track, and week. I select those particular ones and I get ahead. We see now, Tupac's song here, entered on February 26th. Week 1, it was still February 26th, it was rank 87. 1 week later, which is week 2, it's March 4th, it was there. Then March 11th, March 18th. The nice thing about date objects, of course, is that it's not truly a numeric thing. It handles and automatically knows when to rotate to the next month, the next year. If you're working with hour and time, it handles crossing midnight, daylight savings, all that, not daylight savings, but leap years, all that kind of stuff get handled by date objects. It's kind of nice. Okay, so now we have something useful to us, something interpretable. We've converted this weird week measure into time. If I wanted to then plot over time, I could do that instead of plotting over weeks. Right? It's useful. Question on that?
So one question about 2 quote marks that you used. Now I remember the slide number. It was 15. Peak rank. So what are those quote marks?
Oh, yes, I'm being sneaky here. Good catch. Good eye. Okay, if you want in R to use a variable name that has a space in it, you have to put it in what are called backticks. Backticks are up and on the tilde key above your tab on the top left of the keyboard below escape. If you put them in backticks, no matter how long, how many spaces, how many characters, or what type of characters are between those backticks, it treats it as a valid object name. Very often I want to make pretty plots where the titles and things have spaces in them. Backticks let me do that, because normally in R, a space indicates a division between 2 object names. If I put a space there right there, it's perfectly happy to let me put spaces in variable names. Good catch. That's a nice little trick. I took the slide out on that because I was like, I'm short on time. Yeah.
So follow up on that. So if I name a variable like this with backticks, but when I have to use it in my analysis,
Use the backticks.
use backticks.
Yep. You have to put the backticks around it. So like, let's say I wanted to, using conventional R syntax, I wanted to subset it. I'd be like Billboard 2000, $, backtick, peak, space, rank, backtick. You just treat it like those backticks are part of its variable name. It will do it. But when it displays in most plotting, like ggplot, the backticks will disappear and it will just have the space in it. Tables too. So if you want to make nice tables, you can actually have all your variable names have spaces in them using backticks. I do this very commonly for documents that are like auto-generating documents and stuff. I just have all of the data comes in, swaps it to these variable names with those, and then I can spit out all my tables, all my plots, all that kind of stuff with nice spaces and things in it. It's like, yeah, it's kind of nice. Don't have to rename them in line. Great catch. I love that. Okay.
Backtick is the upper left corner.
Yes. Yeah, under the shift tilde. We'll give you, or
It's
tilde
not
is
shift tilde.
not shift tilde. It's just the hit, and tilde is if you hold shift. Yeah. R gets a lot of use out of that key because all formulas have tildes in them, and then backticks are used all the time. They just love that key, right? Okay. Okay. The last main topic for today, and we're working up there on time, so we're going to do okay. Joining data. This is something I know people have asked about, and so I wanted to get it on here, but it kind of builds off of everything else. So sometimes we want to join data. as I did earlier, I hadn't even realized that I left a join in. I'm so used to them just being everywhere. Sometimes we want to make columns that have really like complex criteria or involve summarization of something. So we just want to break them out, do a bunch of operations, and then put them back with the data. Sometimes we need to just join those things back in. It's easy if you want to work with that small subset of variables or whatever. Other times you just need to combine data that were never together in the first place. For instance, maybe you want to combine UW registrar information with police stop records. I did that as a job one time, looking for racial bias in policing for UW policing. It was fun. A little more complex than what's involved here. Often large surveys are broken up into different data sets, and often you just want to merge data from completely different things. Very common if, say, you want to merge on neighborhood data onto individual data. The individuals are nested in neighborhoods. Those neighborhoods are nested in cities. You have city data, those are nested in counties. You have county data merge onto there. You have state data merge on top of that, and then country data you merge on top of that, and then it's over years, and you have all that for that. It's the kind of stuff I do for like my dissertation. So lots of joining. Life is just joining things. Okay. So in concept, before you do any kind of joining, you should think of three things. You want to know which rows you want to keep from each data frame, which columns we want to keep from each data frame, and which variables, which columns in each data set tell you that something in one data frame matches something in another data frame. You always think of those three things? Often, you get so used to it, you're not consciously thinking of it, you know intuitively it's going to happen, but it's nice to be explicit on something, be like, okay, I want this to look like this, and this, and this. I'm keeping these things. This is what the final structure is going to look like. If you know these things, you'll always be able to figure out how to join something, or immediately know it's impossible to join those things. Okay. There are a lot of ways to join things in dplyr. There are many joins. If you are used to SQL, work with SQL at all, basically every common SQL join is represented in dplyr. More complex joins are possible with combinations of these, or extensions like dplyr, database plyr is dplyr for interfacing with SQL databases. Anyway, these are the common joins. Left join will keep all the rows from the first object matched with B whenever possible. So we'll get all the rows that match in B. It will not take any rows that do not match in B. But for rows that are not matched to A or matched in B to A, there will be NAs in those spots, right? And it will keep every column from both A and B. Almost every join operation I do and my students do, 90% of the time it's a left join, because normally you're starting with the big data set and you're adding on something that has less granular units. Usually it's a left join. The next most common join is a full join. A full join will keep every row from both A and B, putting NAs wherever either of them are not matched, and keeping every column from both A and B. I'm not going to go into the detail on the other ones, but there's sometimes very specific joins you want. There's types of joins like anti-join that is just about dropping everything that does match and stuff like that. There's a lot of complex things you can do for special operations. So if you're interested, go into them. Usually, 9 times out of 10, it's a left join. When it's not a left join, the remaining 9/10 of those remaining ones, it's a full join. The other times, it's a special like task. Okay, so matching criteria. When we say that rows should match because they have some columns containing the same value, right? We will need to list these in a by argument in the join. The way it works is like this. If I do not include a by argument, let's say I'm doing left join, and I just don't put by equals, dplyr will automatically be like, okay, this guy probably knows what he's doing. So I'm just going to say that every variable that has the same name in both A and B is probably what I want to match on, and it's going to attempt to match on all of them. Often that works. Maybe that's not the case, and instead you have a bunch of redundant variables in both data frames, but you only want to match on particular ones. You can give it a vector of the variables you want to match on, or the name of a single variable. Maybe there's var1, var2, var3 in both data sets. You shouldn't be naming all the data in your data sets var1, var2, var3, but if you've done this because you're a bad person, this is how you would match on those variables. This would say, I want to match on all identical values of var1, 2, and 3 in both A and B. So a match would not occur here unless var1, var2, and var3 were all correctly matched between the two of them, right? Okay? Maybe you want to match identical values, but the variables have different names in the different data sets. You would say here, okay, I want to match where a var in data frame A is equal to b var in the other data frame, and where a var2 is equal to b var2. So you can give it specific names and a chain of specific names, and it will match on those. So if you don't want to rename your columns ahead of time to do your match, you can just specifically do it in here, and it will match on these, and it will retain the name of the column that was used in data frame A. Okay. Now, if there are multiple matches in a join, you will get one row for each possible match. This is actually really nice, because imagine that you're merging city level data, say, into states or something like that, or not city level, but say neighborhood. All of those different neighborhoods, like you got like 100 neighborhoods, you want it so that every one of those neighborhoods gets all the state data, so you get one row for every single one of the matches and stuff like that, right? You want those redundant ones. Sometimes you do not. If those are special cases, work with semi-joins and anti-joins to get exactly what you want. Yes?
So just to make sure I'm tracking, because you're picking which one is A and which one is B.
Yes.
You should probably pick the one with A that has single records, and the many records should be the B.
Yeah, well, it'll depend. Often with many things, you're going to get the same result either way, but it depends what you want to do.
How do you choose which is A and which is B?
That's arbitrary. Oh yeah, it depends. You just want to keep in mind what things you want to keep and what things you want to drop. So it really only matters if, for instance, you know you have things in A that you don't want to lose but do not have a match in B, then you want to use that as A, right? Because if you use it as B, it won't be matched to anything in A and you'll drop it. So sometimes there's a logic game to it, but if there is a match for everything, the left join is going to give you the same result probably with either one. Yeah. Which is why I usually just use left joins, because I usually want everything. Or I can do full joins, but that's usually the same result too. Okay. If you need to get more complicated than these sorts of options there, do multiple different types of join or break things up into pieces. You can usually figure it out. There's a logic to it. Or learn SQL or interface to like a SQL database with one of the many, many different R packages that let you actually work directly with SQL databases. Like you can write SQL queries in R, send them in, it will put everything together and send it back to you. You can do that. Okay, so quick example data set for doing some joins is the NYC Flights 13 package. I use this for like one homework and a couple lectures in my class. This is a library you load, but it contains 5 different data sets in it. It's every flight that left a New York airport in 2013. It's a huge data set, right? It has a data set of the flights, the specific flights. Another one that is just the airline abbreviation, so the FAA codes for the airports. Airport metadata, so information on the individual ones, including latitude and longitude. So my students like to map them, which is super cool. Planes, so the specific planes. Every plane obviously operates on multiple flights, so there's specific data on the planes, like how many engines they have, when that plane was put into service, that kind of stuff. And then the weather, which is hourly weather data for JFK, LGA, and EWR airports. So you can do all kinds of really interesting stuff, but the thing is, these are all in different data frames. If you want to use any of it, you gotta stick it together. So here's an example of a join. Let's say what I want to know is I want to know who manufactures all the planes that flew to SeaTac Airport in 2013 from one of the New York City airports. I say, let's go into the flights data frame. The flights is every individual flight that went from New York to any airport. Filter down to destination equals Seattle. So now I'm looking at the observations that went from a New York airport to Seattle. I want to select the tail number. The tail number is just that individual plane's unique identifier. Then I left join that tail number to the plane's data frame. Notice inside of the left join, I'm already doing some operations on the plane's data frame. Because the only thing I care about in the plane's data frame is the tail number, what I'm going to join on, and who manufactured the plane. So I have the plane's data frame down to only tail number manufacturer. I join it to the flight's data frame, which is only the tail numbers of planes that flew to Seattle. Join it by tail number, then I count manufacturer. Count is a dplyr function that creates a tally, a table of whatever variable you give it. So I'm tabulating manufacturer. Then I say arrange by descending number. Count generates a variable called n that is the tally, the number of any given observation. So we see most planes that flew to Seattle, 2,659 of them were Boeings, there were 475 Airbuses, so on. You'll notice in this particular data set, Airbus can take multiple values. That's a cleaning thing you'd want to deal with on your own if you actually cared about these data, but the example works. This is me doing multiple operations to each data set, including inside of my left join, and joining the data together and spitting out some result of interest. Cool, huh? Any questions on what I did up there? It's complex.
So if you're learning something like this, you would want to take it one step at a time and like look at it.
Oh, I don't write every single one of these things in one go. I usually write 1 or 2 functions, I see what pops out, and then I add more to it. That's the nice thing about chaining these things, is you just write up to anything before a pipe, run that and see what happens, and you're like, oh, that looks the way I want it to, add another function to it. Run that, oh, it looks like what I want to, add another function. Eventually you've got 80 functions chained in a row, but you do go step by step. If you don't go step by step, you never know where it went wrong. I mean, at this point, with something like this, I would probably write this entire thing out in one go, but I literally do this for a living, so it's like, yeah, it's going like that. But, I anything I'm unfamiliar with, I would never write more than 2 function calls in a row, probably. Yeah, these are, I won't say they're contrived examples. I mean, I actually came up with these and did them, but they are still like, they're being presented as is, where there was a process behind it. I won't pretend that I don't routinely screw up while I'm doing this stuff, right? I'm like, all the time I'm typing stuff and being like, why is this thing screaming at me? And it's because I did something dumb. As I tell my students, that programming is about a failure spiral where success is at the center. Error messages are just those things that guide you correctly down the spiral. So you're like, fail, 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 yes, and down the center. And you just learn to really enjoy that landing in the center, and you just kind of get over the fact that that spiral always exists. And no matter how good you get at it, every programmer spends a lot of time swearing their way down the spiral. It doesn't matter how good it is, because the thing is the things that don't cause you to swear down the spiral, you don't even think about anymore. They're second nature. So your life is always spent in this shitty spiral of hating yourself. But you get so much joy when you solve a problem that for me, it's just it's this constant thing where I like working on it, because the problems are tough, but I know nothing's a permanent problem, right? It's not an indication that you're an idiot. Well, okay, some of my errors are an indication that I'm an idiot. But most of the time, it's a real problem. If you think about it and you can't figure it out, you're gaining something by spiraling down on it. But yeah, this is something like this that definitely you spiral in on what you want. It's iterative.
Another process question: are you doing this all in RStudio? Yeah. And you don't work in Markdown? You just do it.
Well, most of my slides, I'm actually working entirely in Markdown when I make the slides.
Okay.
My own work is almost entirely in scripts because I don't need to produce output documents. And when I generate an actual project, normally my Markdown documents call out to external R scripts. So the Markdown documents usually have very little code inside of them. But they call out to external scripts that do everything. So I normally work with what's generally referred to as a development pipeline. So you actually sketch a diagram where you have your data flows to a script that loads in the data. That spits out to 2 different scripts. One reshapes the data for descriptive statistics, the other reshapes it for models. This script runs all my models. That script splits off to one that generates my results tables, and another one that generates diagrams. Those diagrams get fed into my Markdown document, which formats them here in the Markdown document, and it all gets assembled, but it's a pipeline that you can sketch from the data all the way to a finished document. That's how I do my stuff, and unfortunately I don't have enough time in my classes to teach the full pipeline. I introduce students to the pipeline idea. Some of them just run with it and they get amazing, but most people are just like, oh, that's scary, and they don't do it, and I totally understand, I'm a little crazy with it because obviously I teach this stuff as a job, it's my thing, and I do talks on things like reproducible research, which is all about making reproducible pipelines. I do that, but I'm usually my slides, it's all done, all in Markdown. I didn't even bother doing anything as a script outside of it because I know the stuff's gonna work. These are really simple examples. My other stuff is all scripts though.
So for people learning R, do you start them on Markdown or script?
Oh, my students have to do everything in Markdown documents from day one. They are not allowed to turn in anything in just an R script. They turn in nothing but Markdown documents. By the end of it, they are hardened Markdown users. Everything they're turning in are gorgeous, beautifully formatted Markdown documents, everything in line, only the code shown that I want them to show. That kind of thing. It's amazing how quickly in a 2-hour-a-week class students can pick up how to make beautiful documents and things like that. It takes them about 2 weeks. Yeah. Stuff is not hard to pick up. And you'll see, I drill it into it. If you watch one of my video lectures, they get it hard the first week. I'm like, okay, everything in this class has to be in this format or I don't accept it. Your homework is due next week. 1 credit class. It's the most savage 1 credit class on campus. But I do have though my teaching reviews, I consistently have a 4.9 out of 5 teaching reviews. My class is loved, and I always have 40+ students in it, so it works. But I am very hard on them for a 1 credit class. Anyway, fun times. Anything else? Okay.
Chuck, I just want to be mindful, we did advertise up till 2. So
Yeah,
if anyone needs to go, don't feel like you have to stick around, but Chuck is with us till 2:30.
Yeah, I'm officially done with content except for a preview for the next workshop. Yeah, but if, this is what I'm going to say is, theoretically, I'll probably do another workshop on visualization, maybe. Graphics are fun, one of my favorite things to do. I actually teach ggplot in the second week of my class there, because I try and get people in the cool stuff first. Markdown first week, ggplot second week, dplyr third week, hard stuff later when it's too late to drop. Yeah, we could take all the data we worked with today and visualize it to get some more information on it, to see what it is. So for instance, let's say I take this Billboard 2000 data that I did, and I want to plot it. I want to see what it looks like. This is me taking the Billboard 2000 data. I'm going to say my x-axis is going to be the week, so the week it was on the Billboard 2000. Y-axis is going to be the rank it was on. The group is going to be the individual tracks. So that means I'm going to draw some lines. Each line is going to correspond to a single track's trajectory over the weeks and through the different ranks. I'm going to color it by peak rank. That means I want the ones that hit rank 1 to be colored one way. The ones that did not will be colored blandly because we don't care about them. I'm going to draw some lines, geom line there. I want them to be bigger if they hit rank 1. I want them to be partially transparent. My scale is going to be a logarithmic scale on the X. I care more about the early weeks than the later weeks because most songs don't make it to the later weeks. Scale Y reverse puts rank 1 on the top and rank 100 on the bottom because higher is better intuitively. I put a particular theme on it. My X and Y labels are week and rank. I have manual color scales, manual size scales. I put my legend in a particular place because I am picky and I make its background transparent, right? All these picky things. I get this. This is a plot of the trajectory every song took through the Billboard Top 100, week to rank. Any song that hit number 1 is colored red and slightly larger. What's interesting about this is you can immediately see some interesting stuff pop up. The only reason I could even put my legend there was because there's clearly censoring after week 20 for songs that didn't hit high enough on the Billboard Top 100. So they're dropping data out of there. But this lets you show what is the average kind of flow for songs. There's a couple odd songs that will immediately pop out. You'll see that almost every song kind of goes a nice arc up, sticks to the top, and then drops off rapidly, except for one song that kind of went up and down, and then just shot up popular right at the end. I'm going to look that up and find out what song that is, right?
What song is it?
I have no idea. I forget, right? But you could look into it. You could also look into like where that censoring is, because not everything is censored. See how one arcs up there? So it seems like maybe it was censored on songs that never broke like 45 or something. Weird. But this is what real data are like, right? Sometimes there's stuff is missing. We would not have known that censoring was there very well without plotting it to see it's systematic. Okay. It's the kind of plot like we do in my class. This is a week 4 plot or something like that, you know? So it's not hard. This looks like a lot of syntax. Everything makes sense though. Like every individual component of the plot, it has its own little function that just tacks it on. So much like dplyr functions, you build it one thing at a time until it looks exactly the way you want. ggplot is wonderful like that. Okay, so additional resources if you're interested in more things. That link up there, UW CSS 508, is my intro to R class to University of Washington. All lectures are videotaped. If you want to watch my entire class, L content is available online. Nothing is hidden. All the code that generates my slides is posted on there. Everything is there. R for Data Science is the best textbook on R, and it's entirely Tidyverse based. So all the code in it is like this Tidyverse type stuff. All the ggplot, all the dplyr, tidyr, all that's in there. It's a great book. Advanced R is like advanced R programming nuts and bolts, not Tidyverse. Very good stuff. DataCamp is, I think, the best commercial product solution for learning like R stuff. The tutorials are amazing. It also has other things, not just R. The Python tutorials are excellent too. Swirl is sort of a mini data camp that lives inside of your R. It works very well. You basically install a package and it has pop-up tutorials and you do stuff right in line. Bunch of cheat sheets are linked out of there. That is it. So thank you for showing up and having a good time.
Thank you, Chad.
Yes. Thanks for staying over time.
We recorded, obviously, and we'll have that out in a couple of days. And
Yeah.
So Chuck's here till 2:30, so if you have specific questions.
No.
Oh, and please make sure to sign the sheet at the table so we can keep track of our people.
Yeah, the recordings are always vital because I speak quickly and there's a lot wedged into those things. So, and it's also nice for my students because it means that they don't have to show up if they don't want to see my face. They can just like, okay, I'll look at this stuff later. Yeah. Questions? Doesn't have to do with this content either.
I have two questions about the way you can handle data, because I have always worked in SAS and Stata.
Oh yeah.
So in SAS and Stata, you can actually you make a new variable. You can quickly open the data editor and see how it looks. Because I don't work with big data, but I'd like to look at the data, how it's coming
Yeah.
out. Is there an option here other than heading code?
Oh yeah. So if I have this open here, let's go ahead and okay, let me load. So RStudio has a built-in data viewer, much like Stata's data viewer like that. It works exactly the same way. Theoretically, you could, I don't even know, you probably, yeah, it won't let you edit, which is good, because you only want to systematically edit your data, you don't want to click in, but it works just like Stata's data viewer.
Got it.
Yeah, so you have that. Yeah.
Okay, excellent. A second question was, for example, in SAS, I can make a subset of data and I can save it as in my directory as a separate data set.
Yep.
So from what I could gather here is it kind of keeps on adding everything into a single file.
They're actually separate objects. You want to see how, so if I say this gapminder data, let's say I want to get, I'm going to create an object called Serbia, which I'm just going to take gapminder, yes. Serbia. Okay, so I now have this Serbia object up here. If I only want to save Serbia, I literally can just say save Serbia and file equals Serbia.r data. Now there's an object in my working directory right here, which is a .r data file. Any named object in R could be saved, or any combination of named objects. R is just the main difference between R and like Stata, obviously, is that you can have an arbitrary number of data sets open at the same time, where Stata is like kind of a one data set thing with limitations. This, every object is its own thing, can be saved, you can do anything you want with it. You can even save individual plots and stuff that way.
Right, so once it's in my working directory, I could go to another project on R and I could pick this data from there.
Yep. Yeah.
Wonderful. Thank you.
Yeah. Anything else?
I have a question.
Yes.
So you showed us sort of how to, some steps that one would go through after you import data to just sort of check it. What is the sort of advice that you give to people who are really steeped in using spreadsheets to learn how to trust the process? Like, ultimately, when I sit down to do something, if it's important, I just can't follow through in R because I just don't trust, because I'm so used to being able to see things.
Yeah, so one thing is that, I don't trust, do you need to pull the equipment or do you need to? Okay. So, I don't trust anything, especially not anything I've done. So the thing is I don't, but the thing is if you make it, you check it, you make it, you check it, you make it, you check it, you always check. And that's why the heads, the tails, every single thing I run like is followed by a head or a tail. I display, I always look. And the reason is because I don't trust. I always used to work in Stata where I always wanted to see that thing. You can open up a viewer window like I did here and you can look every time. I don't. But the thing is that you know with code, if it worked once and you do the exact same thing again, it will work again and it's perfectly fine. So I do only have to check once each time. And that sort of thing I do. And then, you always check though. You never just trust it, because that's how you make weird little mistakes and you miss them. You always look. But if it worked one time, when you run it again the next time, if you didn't change anything, it's gonna be the same. That's the kind of thing. It's not really like faith. It's more like the deep philosophical understanding that computers are not good at doing different things when told to do the same thing. They just do the same thing.
Right.
And that's kind of it. But I started in SPSS. I went to Stata. I taught Stata for ages, and I always check everything. And now in R, it's like I still do my checks and stuff, but once something is set and it's set in stone, it works. It's always going to work.
Yeah. That's where I have to get to, I think, to really start using it.
Yep. And then the other thing is you just get used to it. It's like anything else, you just get used to it. My students, I have tons of students come in and say the exact same thing where they're used to working in Excel or something like that.
Yeah.
They just get used to it.
Yeah.
The main thing that usually gets people is that it's so slow and hard to work in Excel compared to doing so many things in R that eventually it just like They ended up, their desire to work in Excel is overwhelmed with how easy it is for them to work, especially, God, if they're used to, like, say, doing statistics homeworks and copying and pasting things into a Word document.
Right.
Once they figure out, like, Markdown docs and they have to stop copying and pasting it, they're just like, okay, I don't know if I trust this thing completely. Oh, but man, it saves hours. So, there we go.
Thanks.